In this video, we finish up with the fundamentals of probability. This includes things like conditional probability, independent events, and mutually exclusive events. Enjoy. Let's get into it. Cool. So for the remainder of this class, we're going to cover the things that we did not finish up when it came to fundamentals of probability. So starting with this idea of conditional probability. So the whole point here is you could have a certain scenario, you might be contrasting one or more events to each other. Conditional probability is this idea of essentially restricting the sample size that you look at. So in the example that I have, actually let me double check. Yeah, okay, I'm screen sharing everything. Good. In the example that I have here with the Venn diagram, we have a six-sided dice being rolled, numbers greater than 3 and even numbers. Those are the things we're tracking as far as events are concerned. So all the numbers greater than 3 are on there, all the even numbers are there, and then everything else will be on the outside of the Venn diagram. Now, from there, we come across a situation we have a conditional probability. We have to find the probability of getting a number greater than 3, given that we rolled an even number. So that keyword, given that, implies that of our total sample size, we're only going to look at the possibilities where the number was already even, because we're told the number was even. So instead of saying rolling a number greater than 3 would just be 3 out of 6, so a half, you're now looking at only of the even numbers what is now the probability of rolling a number greater than 3. So you've got 3 possibilities here, 2 of which are also greater than 3. That's going to give you a 2 out of 3 chance for the conditional probability specifically. As far as notation goes, the probability that you're looking for is the thing that goes on the left-hand side of this pipe, of this vertical bar, and the thing on the right-hand side is the condition or the restriction on your scenario. Fair enough what I've described so far?
Yep.
Sweet. As far as a formula for how that works, any generic A given B can be found by finding the intersection and then dividing by the probability of your conditional. And that's exactly what we did. We had our intersection, which was here, and then the conditional, which was all of that. I've just written it in terms of the probabilities of each of those things occurring rather than the raw number of those things occurring. That's pretty much it. So sometimes you don't have a Venn diagram. Now you could create a Venn diagram for sure to get an idea, but under these circumstances, if you don't need to, it'll be a bit faster. So we have this scenario, we have 24 total students, 12 of which study physics, 20 of which study math, 8 study both. So you can imagine how you would create a Venn diagram out of this anyway. Alternatively, you could just go straight for the formula, which is figure out the intersection and then figure out the probability of your conditional. In this case, we said, given that a student studies physics, what is the probability they also study math? So before I dive into the specifics on this example, one of the things you might notice is that the wording is back to front here. Given something, probability something else, versus saying probability of something given something else. So you can interchange the way those words or those statements are written. Basically, whatever word comes immediately after given is your conditional. That goes on the right. Whatever stuff comes after the word probability, that's on the left-hand side. That's the thing you're trying to solve for. So that's how you can know which to put where, essentially. But okay, we need the intersection and we need the probability of the conditional. Well, we know 8 out of a total 24 study both. That's going to be our intersection. And then our conditional we knew was physics. So again, out of the 24, 12 studied physics. So you got a 12 out of 24 there. From here, you just perform that division. So intersection divided by conditional. At this point, it's better off using a division sign rather than stacking fractions. A little bit easier to see what's going on. You'll notice that every time you do this, as long as you don't simplify what you had to begin with, the denominators will cancel out. So just divide by 24, they cancel all the way down as long as you don't do any simplification there. So better off doing it that way. That way there's less effort in the simplifying afterwards. When you do that, you're left with 8 over 12 or just 2 over 3 as your probability. And as I said before, yeah, you could create a Venn diagram out of this and then do the same thing we looked at earlier. It's a personal preference thing. This is a little bit faster though. Okay, so another place where conditional probability shows up is in tree diagrams. Anytime you have a tree diagram, the probabilities that are along those branches are conditional probabilities. You only get to this spot on the branch if you got past A first. This itself is a conditional probability. It's conditional based on taking branch A. So in the example we have here, we have two assembly lines, assembly line A, assembly line B, and motors on those assembly lines have a percentage chance of being faulty. We're told 5% on line A are faulty, 8% on line B are faulty. So the wording around that implies that it had to go through line A before it had that chance of being faulty, or it had to go through line B before it had this chance of being faulty. That is conditional. I have a bit more information. So in 1 hour, we got 40 motors on line A and 50 on line B, and then they're all just sort of put in a box and we pick one to sample, and we've got to figure out is it faulty or not, or at least what's the probability of it being faulty. So from there, you could set up a tree diagram. Again, you're going to have line A, line B, faulty, not faulty. As far as how you put the probabilities in here, I'll let you take a stab at it. Maybe starting here. Why are these 4 out of 9 and 5 out of 9, respectively?
Because well, okay, so like in total, there's like 90 motors, and then like if you write them as a fraction, it's like 40 over 90 and then 50 over 90. It simplifies to like 4 over 9 and 5 over 9.
Bashed it. Yeah, absolutely. Then from then on, the rest of this isn't too bad. Right, 5% shows up as 0.05. Then you've got the complement of that. Same thing over here.
Wait, I have a question.
Yeah.
So for like conditional probability, would you advise like, drawing like a tree diagram or like, just using the formula to solve it?
Depends on the question. So I've always gone where possible using the formula here. Although recently I've been doing like year 10, year 9 math, and I've actually found that these Venn diagrams are also pretty nice to work with because you can visually just have a look and see, I've only got to look within this section and then grab the intersection from that. Venn diagrams work well. Even two-way tables work well. Tree diagrams, these are pretty specific. This is more so if you have like a sequence of events. Trying to do a tree diagram for this, like this dice roll thing, that'd be pretty tough. So it would depend on the question, really. But this formula always works. That's just a global formula no matter what. That's why I typically prefer it. But recently I've found that Venn diagrams and the two-way tables are pretty useful for that as well. We'll see an example of a two-way table next. Yeah. So as far as how the two-way table stuff would work, in this case we have given younger than 30, probability of medication. So younger than 30 would be this, and then yes to medication. Given means it's a thing on the right, probability is the thing on the left. And so it means we need the intersection. That's never going to change, but the denominator is going to end up being the conditional. Now, the shortcut for two-way tables is if you have this full thing already filled out, or if you fill it out yourself, the way it works is you first look at your conditional, and then you look at the total of that. This is now your max sample size. That's your denominator right there, 520. Then, within this column, you look at the intersection. If you want the yes one, you pick the 200. If you want the no one, you pick the 320. That's all it boils down to. So you'll notice I do it the long way, which is calculating each individual probability, but you can shortcut the process by going straight for the raw numbers here and here. So 200, 520, you'll notice when you do the flip, the thousands will cancel down, and you're left with that 200 over 520. That's what I detail in solution B here, the shortcut. But otherwise, if you forget that, it's fine. You can do the normal probability calculations and then just chuck it through the conditional probability formula. Another place this comes in handy is to solve like intersections. If you have a whole bunch of probabilities and one of them in there is a conditional probability, then you can use that formula to rearrange for the intersection portion of it. So we have probability of A, probability of B, and B given A. Now, B given A, we can expand out using that formula to just being the intersection divided by the conditional. So divided by probability of A in this case. We care about this intersection. Now, it's worth noting that whether I say B intersection A or A intersection B, those are the same thing. So if you have this, don't feel like you got the wrong thing. It is the same. But okay, multiply both sides by probability of A, and then that is your intersection. So all you got to do is replace each of these terms with what they are, and there's your intersection. That's about it, really. So it can be used for solving these kinds of things. You might get tables of data where you might have to do conditionals with, tree diagrams. The tree diagram thing is really only here just to explain that these branches are conditional probabilities, not necessarily because it's strong for solving conditional probabilities, like in a broad sense. It's just there to say, hey, these are conditional.
All right.
Yeah, that's about it on conditional probabilities. Anything to clarify before we move on to the next few topics?
No, I think it should be good.
Easy. All right, independent events. So now that we know what conditional probabilities are all about, independent events basically say the probability of one thing, given that another thing has occurred, should be the same as the probability of that original thing. So basically it means it doesn't matter if B happened, the probability of A is going to be the same regardless of if B happened. And so that's one way of proving events are independent. If the conditional is equal to the regular probability, you can say those are independent. The other way of proving it is by calculating the intersection and each of these individual probabilities and seeing if those are equal to each other. So these are the two ways you prove independence. So if you wanted to prove independence in this table here, a couple ways you could do it. This first solution I'll show you is calculate the intersection and then the individual probabilities, compare those to each other. So the good thing about this is you have a fair bit of freedom with it. So this A and this B, whether you call this A and this A dash or this A and this A dash, it doesn't really matter as long as you're consistent with your choice. So
wait, so in the like in any SAC or like when they say this sort of question was given, right?
Mhm.
And then like so do we need to state that probability of A is equal to like males and like probability of B is equal to females, or can we just write like the male and female inside like the brackets?
yeah, exactly this.
Oh,
Yeah, well, as in, like, this is the global, just broad formula.
okay.
The way you write it in your notes is like this.
So like you don't need to state the formula first and then do all the calculations.
I mean, you can, but just state this formula versus this formula.
Oh, okay.
They're the same thing, but one of them uses the terms for the question rather than just broadly speaking. But yeah, that's about it. The good news is you can pick any pair you want. So you can do male intersection movies, you can do male intersection music, female intersection music. I've done two different pairs in the notes just to show you. It'll give you the same thing either way. So there's a fair bit of freedom there. In this case, I've chosen male movies. The intersection there is going to be 75 out of a total 700. Simplify, simplify, simplify. And then you just compare to the right-hand side. So probability of male, 525 out of 700. Oh, sorry, male's over here, 300. So 300 over 700 is going to be your male. And then movies was this one. So 175 over 700. That's that. Male, movies. If you multiply these two things together and compare that to the intersection we found earlier, we find they're the same thing. So, because those are equal, you can call those events independent. I won't go through in much more detail here, but suffice to say, if you picked, for example, female music, when you get down here, the numbers won't necessarily be the same, but the fact that both sides of the equation are equal is the thing that matters, not the actual numbers themselves. Alternatively, you could go through the other approach, which was do the conditional and then compare it to probability of A. Now, this ends up being the exact same work. This is more so just for whichever makes most sense in your brain. Because to calculate this conditional, you still need the intersection and you still need the other probability. Like literally all you have to do here is multiply both sides by probability of movies and you get exactly the same working out as before. So really it's just a personal preference thing. You'll see the intersections get calculated, the probability gets calculated here. This one just ends up taking a bit more time because you smash together things all on the left-hand side rather than spreading the load across two different sides of the equation. It's sort of whatever. Do you want to see that in any more detail, or are you happy enough that that's the same thing?
I'm fine.
Yep. If you want to disprove independence, it's the same thing. You're calculating the exact same terms, but now left-hand side is going to be different to right-hand side. Now, where it mostly comes into play is when the probability is told to you as independent, and that actually becomes important for solving the thing. Specifically, I found around the union equations. That's where it becomes a bit more important. So we're told that events are independent, so owning a pet is independent of owning a car, in this case. Probability of car is 0.75, probability of pet is 0.25, and we want to find the union of those two things. So what's the likelihood to have one or the other or both? Now, the union equation would tell us that we need probability of pet plus probability of car, and then minus the intersection of those two things. But because the events are independent, we can now figure out this intersection. Whereas normally, with the information provided, if we didn't say it was independent, we wouldn't really be able to do this. But because the events are independent, we know that the intersection is the same thing as the product of those two terms. And so it just simplifies down here. From there, you just plug and play the terms you need. Clear enough how this turned into that? Yep. On CAS, I remember this one being tough. Okay, so sometimes they'll basically branch into quadratics at this point here. And this is kind of like those questions where you're finding maximum or minimum value. You'll notice it's the minimum possible value of this union. You actually treat this like you would for applications of quadratics, where you figure out, okay, here's the thing I need to minimize. So first things first is find an equation that describes that thing. So it's like, okay, I've got a union. Here's my union equation. That's all well and good. But issue is I have three terms in here, whereas if I want to graph my quantity, whatever it is, I need to only have one term in there. And so that's where the second equation comes from. In the context of quadratics, it was usually like a perimeter equation or some other thing you could do to rearrange. Basically, point being, you take that second equation, or I guess in this case the first equation, rearrange it to get one of those things on its own, and then substitute. So in this case, well actually no, in this case I didn't even rearrange. We just had probability of A plus probability of B. So you could directly slide that in as 0.4. There was no rearranging super necessary there. Now from here, we're told the events are independent, which again means this intersection can be rewritten. Probability of A, probability of B. So we've gone from having 3 variables down to 2 now. This is what we do our rearranging. So either rearrange for A or rearrange for B. It doesn't really matter. All we're doing is cancelling one of them through the rearranging. In this case, I rearranged for A. So everywhere that I saw A, I'm going to replace with this. simplify, simplify, you have essentially a quadratic, a squared term, an x, and a constant. So you plot that quadratic, minimum value is always going to be at a turning point. And so from there, you just want to figure out the turning point of your function. I've used the derivative approach from calculus. You could do axis of symmetry, you could do whatever you want to do for turning point of a quadratic there. And so what's worth mentioning here is when you grab that turning point, that is an x value. The actual value of the minimum of that thing is the y value at this spot here. So in this case, my x was the probability of b, so I'm just going to sub that back into my union equation and then get the actual minimum union there. How was that? Was that an interesting one?
I'm kind of stuck on like, when we like derive the equation, could you like explain that part?
Derive as in derivative or derive as in create the equation?
Like create the equation.
Yeah, okay. So from here, we're just starting with stock standard union equation. From there, we had this term or this equation in here which said probability of A plus probability of B is 0.4. I have this thing here that says probability of A plus probability of B. So instead of writing that, I can write 0.4. Cool so far?
Yeah.
Okay. Now from here, we have an intersection. Normally, we can't calculate those, but because we know it's independent, we can. So independent just means splitting that up into each of its components, the A and the B, as a multiplication. Cool there? Okay. Now, we can't yet plot this. This is like saying y equals 0.4 minus z times x. Right, we've got two variables in there. We can't plot that just yet. So we need to figure out a way to rearrange this to only have one variable, either probability of A or probability of B. This is where you go back to the first equation that we had. So you can rearrange this thing. So I've copied it over down here. Rearrange it either for probability of A or for probability of B. It doesn't really matter. So when you do that, you'll get a statement that says probability of A is equal to 0.4 minus probability of B. Here's our union. This is the thing we care about. If I replace this probability of A with this, that's what this looks like.
Okay.
And then from there you get your quadratic, so on and so forth from there. Clear enough now?
Yeah, I get it. But like, what's the derivative for?
For turning point. So this was, yeah, that's what that was for.
Oh, okay. All right.
Anything else in here worth going through?
No, it's all good.
Yeah, this is like the toughest, by the way. This would be like a 3 to 4 marker. But this is the kind of thing where, honestly, independent events sort of show up a fair bit in these longer questions because it gives you a way to solve the thing where you otherwise wouldn't be able to. But okay, so very similar to independence is mutually exclusive events. It's just another way of describing the relationship between two different events. Now, mutually exclusive events just means it has no intersection. So that, so the two sets are disjoint. They don't touch as far as the Venn diagram is concerned. As far as an example in real life could be a deck of playing cards. So we have the event ace and the event king. All right, these are two separate things that cards could be. There is no intersection between those, though. You cannot have an ace of kings. So mathematically, the intersection of ace and king, that probably would be 0. And so this is the only thing you need to know for mutually exclusive events. Probability of the intersection is 0. So if you need to prove mutual exclusivity, you're trying to prove the intersection is 0. That's pretty much it. So one interesting question I actually came across a little bit ago was this one here, which is if that conditional probability is equal to 0, can these events be mutually exclusive? Bit of an odd question. When you can only really get an understanding of this when you expand that conditional probability. So the fact that A given B is equal to the intersection divided by the conditional tells you that the only way this will ever equal 0 is if that intersection is 0. Because this denominator won't do anything to make it 0, ever. Only way it's going to happen is from the numerator. Cool.
Okay.
Okay. Proving not mutually exclusive, it's the same thing, but just from a different perspective. This is also kind of unique, so we'll go through it anyway, just so you can see a different take on it. We're told probabilities A and B. Can these be mutually exclusive? Now that's really interesting because you don't even have to know anything about A or B to figure out that they may or may not be mutually exclusive. So events are only mutually exclusive if you have the intersection being 0. So as long as a union is possible, and it is, because any union is possible, having one thing or another, the union equation always expands out to having an intersection in there. And so if you were to plug in your 0.5 and 0.7, you're going to have 1.2. Now, the only way this can be mutually exclusive is if your intersection is 0. If the intersection is 0, you're left with 1.2. So probability being greater than 1, bad thing. This intersection needs to be at least 0.2 for this to ever work out. Clear enough?
So like, if we consider the probability of the intersection between two things to be 0,
Mhm.
and then we add the two different probabilities, and if it turns out to be greater than 1, we say that these events are not mutually exclusive.
Yeah, precisely.
Right?
Yeah,
right.
Exactly right. Yeah.
Right, sweet.
Okay. And then as far as how you can solve mutually exclusive events, if you're told your events are mutually exclusive, let's see, I haven't seen this for a little bit. Probability of x is the same as probability of y dash, so both of those are 0.4, and I want to find the union that we have here. So you'll notice unions kind of show up a fair bit for mutual exclusivity, for independent events, and it's simply because both things are talking about how the intersection works. One tells you the intersection is the multiplication of the two things, and the other tells you the intersection is 0. So if you expand out this union, it ends up looking like x plus y dash minus the intersection of x and y dash. Mutually exclusive means this is 0. We have x, we have y dash, they're both 0.4. Add them together for 0.8. Happy there?
Yep.
Cool. All right, so that is all of those. So we have conditional probability, which also works a fair bit with intersections. Independence, mutually exclusive, whole bunch of stuff there. Now, historically, people really have a lot of trouble with conditional probability. But is there any of the questions we've had a look at so far that seems to be harder than that you'd like to have a look at?
I think it's fine for the most part.
Mostly fine? Okay. So we'll do some conditional probability stuff. In fact, I'll do a screen grab of this. That way you can at least refer to the summary for any guidance. And we'll just go through a few questions in here just to make sure you're able to at least apply the knowledge, because if you can get conditional probability down pat, you'll beat like 80% of people, probably even 90%, because a lot of people really struggle with this, at least in my experience of tutoring.
Okay.
All right, we'll start stock standard, start from question 1. We kind of already looked at a very similar question at the very beginning, so this will already be a touch revision. I'll let you have a read of that. If you want me to work through it with you, let me know. Otherwise, feel free to try it on your own.
All right. Okay. Is the answer 1/2?
Not quite 1 over 2, so it should end up being 1 over 4.
1/4.
Uh-huh.
Oh.
So, do you want to have a look at it again, or shall I start asking you a few questions about it?
Wait. I think let me look at it again.
Yep. Yeah, go for it. Any luck?
For some reason I'm getting like 1/3. I don't know
One
how.
third this time? Okay. Let
Yeah.
me walk me through what you're doing. So what's you see this question, first thing comes to mind is
I drew like a Venn diagram.
yeah, okay. Brilliant. Good start. Alright. So I guess now what's in our Venn diagram? So we're gonna have rolling a 6 and number greater than 2. Which side did you have what?
Okay, so like on the left side I had like probability of 6.
Yep.
And right probability of anything greater than 2. Yeah.
Yep. Okay, cool.
And then outside that I had like 1 and 2.
Yep. That sounds good.
And then inside 6 I had like just 6.
Over here?
Yeah.
That's probably why. So 6 should be in here.
Ah.
Because it's also greater than 2.
Then for like the probability of 6, what would you write inside that circle?
Nothing goes in here.
Nothing goes in there.
Yeah, only the number 6 can be in here. So if you fill in every number 1 through 6, it'll be all this. So 1, 2, 3, 4, 5, and 6. So not everything in the Venn diagram will necessarily exist.
Okay. That's probably where I went wrong.
Yeah, no, that's fine then. Do you want to finish it from here or keep going like this?
Mm, oh, yeah, we'll finish. Actually, we'll keep going.
Yep. Okay, so when we're looking at our conditional probability, the probability of, in this case, it was probability of a 6, given that we have a number greater than 2. That means when we're focusing on our Venn diagram, we only care about this as our full sample size. Okay?
All right.
Now, that means looking within here, what's the probability of rolling a 6? Well, we got 4 total events. One of them is a 6. So you're going to have a 1 out of 4 from that. That's how you solve with Venn diagrams, essentially. You look at the
Wouldn't
number.
it be 1/6? Because like in total there's like six, like a sample of six.
Yeah, so in total, the full sample size would be a 1 out of 6, but yes, that's correct. That's if I had just said find probability of getting a 6. Now, because we're told the number was greater than 2, we can't include numbers 1 and 2 in our sample size. So we can
Okay.
only look within this box. That's all we're allowed to look at.
Okay. All right.
Cool. So that's the Venn diagram approach. Whatever your conditional is what you highlight, and you just ignore everything that's not that. You just cut it out, erase it, whatever you got to do to make sure you don't use it. From there, every element in here becomes your sample size, and then only the thing you care about, which is always going to be an intersection, will go on your numerator.
Okay. All right.
That's the Venn diagram approach. The other approach is to use the conditional probability equation, which would be the intersection of those two things, so intersection of 6 and greater than 2, all divided by the probability of being greater than 2. So the probability of the intersection, so 6 and greater than 2, you got one element out of a total 6, so 1 out of 6, and then you're dividing that by the probability of greater than 2. So you got 1, 2, 3, 4 numbers out of a total 6, so 2 out of 3. Do that division, 1 out of 6 times 3 over 2, and that's going to give you 1 over 4. Yep.
Yep, I got it.
Cool. Okay, a couple of ways you could do that. Now, there's a question too, which is pretty much identical. Do you want to give that one a shot just so you can be sure you can do it yourself, or move on to a different one?
Yeah, sure. We'll give question two a shot.
Sounds good to me. Give it a crack.
All right. Is the answer 1/3?
1/3 is correct. Yeah. There you go. Clear enough why that is?
Yeah.
Nice. Okay, so that's those. Those are very sample space style. You got to figure out what the possible elements are to begin with, and then maybe put them on a Venn diagram. In this case, there's a bit of addition slash subtraction to be worked with here. So have a read of question 3. See how we go with that one.
Is the answer 7 over 12?
The numerator is 7. I know why you put the 12 there. The 12 isn't quite right, though.
Oh, okay. Where did I go wrong?
What was the 12? Something about that 12. 12 is not the total number of people that do piano. I'll say that much. What is the total?
Wait, isn't it?
No,
Isn't it 12?
no.
No? Um, okay.
Some play both. 7 play both.
So that
12.
would be the intersection, wouldn't it? Seven
Yeah.
is the
hmm But
intersection.
but it's also in the piano section, isn't it?
Yeah.
So this group here, 7 play both violin and piano. So that counts for 7 piano students and 7 violin students. Then there's a further 12 that only do piano.
Oh,
Yeah, there you go.
oh,
So it's not just of the only pianos, it's just people who play piano, blanket statement.
okay.
So new total is going to be 7 plus 12, or 19 as your divisor. But yeah, so I'm assuming you did the Venn diagram.
Yeah.
Yeah, so it's kind of like what we did up here, which was, if you go to the handwritten bit, we didn't just say denominator was 3 elements. We said denominator was 4 because we have to also include the stuff that's in the intersection as well as our new sample space. Cool?
Mm-hmm. Yeah.
Okay, so that's that. This one's very similar to, I mean, it is weirder actually, because your conditional is now something really strange, which is given both dice show the same number. Yeah, okay, this is unique as well. How would you go about this? Yeah, okay. I've got no idea how it would work. Have a think about it. If you get stuck on how to represent that, let me know.
Okay. Is it 1/18?
Not 1 over 18, unfortunately. Not too sure where you might have got 18 from. What was your approach?
So well, the question asks like, given that oh shoot.
Oh, did you misread
I
it?
didn't Well, the question asked like given that both the dice shows both the same number and like it
Mm-hmm.
asks what the probability of six is.
Mm-hmm.
I did a mistake and like just tried figuring out like probability of rolling a double six.
Oh, okay. Then just double six. Yeah, no, okay. Six. Well, that'd be 1 over 6 times 1 over 6. Yeah. That should be 1 over 36 in that case.
Oh.
But it's fine. Yeah, so now a conditional, right? So double six, but you're only looking at the sample size that is numbers that are doubled already.
Hmm. Mm. Let me just try reattempting this question.
Yeah, absolutely. It'll help when we know what the question's asking. I'm sure you get it.
I'm not sure how to do this.
Yeah, that's okay. So, a couple of ways. The way that I was thinking about it myself, just trying to figure out the best way to go about it, and it's probably what I'm about to show now, which is another Venn diagram approach. So the conditional was that we have doubles, so same number. So one of the events we're going to keep track of is all the possible doubles in the scenario. And the other event that mattered was getting a double six, so sixes. Now, when we think about the sample space for doubles, so we'll just say D for doubles, what are the possibilities for the doubles?
Like double ones,
Yep.
double twos. Yeah.
Yeah, so on and so forth. 5, 6, all doubled like that. Now, only one possibility for double sixes, and that's getting the 6. Now, what you'll notice is the 6 is common to both of those. And so that goes in the intersection spot, the double six possibility. And then everything else, 1, 2, 3, 4, 5, those are all there. So when we're looking at this conditional probability, which is only looking within the doubles, what's the probability of rolling a 6? We have 1, 2, 3, 4, 5, 6 total elements, one of which is a 6. So 1 out of 6. Bit tough. That's only the way that I thought about it after thinking about it a fair bit. The way that immediately came to mind was using a two-way table. So you could literally go and think and look in the entire sample space of numbers that could be rolled. So 1, 2, 3, 4, 5, 6, and then just, you would do your 1, 1, 1, 2, 1, 3, 1, 4, fill this entire thing out, and very quickly you'll realize that the only thing you actually care about is the diagonal. 3, 3, 4, 4, 5, 5, 6, 6. Because you could have the full sample size. It's saying, okay, now look only at the doubles, which would be along this diagonal, and then which of that sample size, which of them is a double 6. So this was the first thing that came to mind, which is fill out this entire thing, cut out the bit you care about, and then within that, do your probability. Or you could do maybe a bit harder to conceptualize, but it uses the same tactics you've used before for the same thing. Clear enough on both approaches there?
Could you explain like the two-way table one?
Yeah, so basically the two-way table is just, here's all the possible dice rolls I could have. I roll one set of dice, I roll another set of dice, and I could fill out this entire thing. So this would be like, maybe we'll say this is dice 1 and this is dice 2. This would be dice 1 is 1, dice 2 is 1. Dice 1 is 1, dice 2 is 2, and so on and so forth. You could just fill out this entire table of 36 elements and get every possible dice roll there. Is that fair enough so far?
Yeah.
Now, the conditional, so it says given both dice show the same number. So that means that we're taking this massive sample size that we have and restricting it to only where the dice show the same number. And when you fill out the full table, you'll notice that the only same numbers will occur on the diagonals. And you can kind of see that already as is. Like it's only going to be the 1, the 1, the 2, the 2, the 3, the 3. It's going to be along that diagonal. Cool there?
Yeah.
Now, that means that we only care about this now, within this diagonal of 1, 2, 3, 4, 5, 6 elements. That's our new sample size. We ignore the rest.
Okay. All right.
Okay, that's clicked it?
Yeah.
Nice. So yeah, obviously this one's a bit more brute forced. You would just chuck everything into there. This one, a little more, maybe a little more refined. As you do it, you'll see you wouldn't really fill out the full table. You just want to get the pattern. But okay, starting to see why conditional probability is the hardest of these. It's definitely on the tougher side. But okay, so that's chapter 9F of Unit 1-2. If you have all the other books... Oh wait, no, I don't have it written out, do I? Yeah, I just got the Unit 1 and 2 ones. I'm working still on getting all the Unit 3-4 plus Jacaranda spots on these as well. And you should have access... Actually, do you know where to grab the Jacaranda and Unit 3-4 books?
Our school doesn't use Jacaranda anymore. We use Cambridge.
Yeah, no, that's fine, but part of this gives you access to them, so I was curious to see if you see that or not. What I'll do is I'll drop a link in this Zoom for it. That way you can just quickly copy it